Hi, so we're going to talk about Year 2 trig. This is specifically for Edexcel, but obviously the techniques will still apply to any exam board. So to start with, I've just listed kind of all the main formulae that you're going to need, and I'm going to put in red the ones that you actually get given in the book. So you should still know them off by heart, to be honest, just because you'll need to recognize them in reverse in certain situations. The double angle formula, really important, especially with sine and cos. They are not given. You can derive them from the addition formula if you want, right? If you put b equals a in sine a plus b, you get sine 2a. But again, you should just know these really well and be able to recognize them. And for cos, obviously, we have the three different formulas for double angle. And depending on the situation, you might want to use either one. So you have to be aware of that as well. We have these three, obviously very big as well. Make sure you know them. I always say once you know this one here, the next one beneath it, you sort of take the co of everything. So tan becomes cotangent, sec becomes cosec. So it's quite easy to remember. And I put the tan ones down there because, like, you do need to know them, but they're not as common as the others. So focusing on identities and equations, and maybe another video could do some modelling. But I want to talk you through some sort of like how I go about solving identities. I've got one here. So this is a very common layout for a trig question where you have part A, prove an identity, part B, solve an equation, where you recognize part of that equation from the identity. Really common structure. And you can answer both parts completely independently as well. So when I look at this identity, first choice is which side I'm going to start from. And you want to start from the side that looks like you can do something to it. Anytime you have a fraction, like adding fractions, that's a really good thing to be able to do, because you'll get some kind of cancellations when you make a common denominator. So adding fractions, that's where I'm going to start. So cos 3 theta, so left-hand side, is identical to, and then it's going to go. I see fraction addition. Make sure when we do identities, we're not working on both sides at the same time or ever changing the value, right? We're just starting on one side, ending up at the other. So if you just make a common denominator here, or however you want to add them, I get this. And I'm always bearing in mind what I'm aiming for. The key thing to look out for in year 2 questions is, do you have theta, 2 theta, 3 theta? It's going to make a difference, right? What I'm aiming for is something with 2 theta. What I have now, I've got 3 theta, and I've got theta as well, actually. So it might be a bit of a problem. The quickest and easiest way to do this is to actually recognize this is an angle addition formula. I'll write it down. This is actually cos 3 theta minus theta, if you think about the angle addition formula. So you can just straight away write cos 2 theta, and then you're pretty much done. I do want to show you how to get the answer without using the very quick way, because like you may not find that in the exam, right? And it's okay. There's usually going to be more than one way to do this. And as long as you're not making any mistakes and you're taking steps that take you towards the right-hand side, you shouldn't really go wrong. You should still end up there. So my step is going to be, well, I know I need to get this 3 theta down to 2 theta, right? Because there's no 3 theta on the other side, and there is a 2 theta. So I'm just going to rub out this really efficient way of doing it and do the long way instead. And I'm going to write cos 3 theta. I'm going to think of cos 3 theta as 2 theta plus theta. It's quite a common thing to do in trig if you're given 3 theta. And just use the addition formula here. So that's going to be cos 2 theta minus sine 2 theta sine theta. And you see how quickly I can just do the addition because I know the formula. You should be at that same level. You shouldn't be wasting your time looking through the booklet, in my opinion, here. Okay, common denominator. And again, I know I'm making the right steps. Don't be afraid, right? It's looking more like the right-hand side because you've now got no 3 thetas. So just filling the rest in. And be prepared to sort of go back and start again, but also be aware that you're probably going to get something cancelling and something nice happening if you can spot it. In this case, there's a very obvious cancellation, right? With a plus minus the same term. Just going to cross that through, so there. And when I look at what I've got left, okay, cos 2 theta cos squared theta and cos 2 theta sine squared theta, you should always look out for this kind of pattern. I'll write out in full, but where I have the same thing, cos 2 theta, once multiplied by cos squared and once multiplied by sine squared. And since I've got an algebraic fraction, I might also be thinking of factorising, right? And I can factorise the top. And if you do factorise, you get something very nice. Okay, we get our nice sine squared plus cos squared, just giving us 1. Also, my 2 theta down here somehow changed into a theta. So that's not the best. Sorry, my theta changed into 2 theta. Okay. Still working down the page. Okay, this is now cos 2 theta over sine theta cos theta. It's looking good. It's looking pretty close. I'm just going to remind myself of what I was aiming for. I'm not allowed to use it like directly, but I can keep it in mind, right? 2 cot 2 theta. Okay, so I'm aiming for 2 cot 2 theta. It can be helpful to sort of write out pretty much everything just in terms of sine and cos. I often do that in Identities. So this would be 2 cos 2 theta over sine 2 theta. And I can see, based on what I've got and what I'm aiming for, the numerators are pretty much matched up. There is a 2 there, but hopefully that'll sort of sort itself out. So I need to look at the denominator. And you should be able to recognize, if you know your formulae well enough, that on the bottom I have sine theta cos theta, and over here I have sine 2 theta, and we know those are related, right? I know that sine 2 theta will be 2 sine theta cos theta. It's often quite helpful to sort of rearrange this and just get sine theta cos theta by itself. That's going to be 1/2 sine 2 theta. And I can see this is the right thing to do because it links together what I have and what I'm going for. So let's just fill that in. Cos 2 theta over 1/2 sine 2 theta. And this is, if you divide by the half, you get a 2 cot 2 theta, which is the right hand side. And I'm done. Okay, so not the quickest way, but just to show you, you can't really go wrong as long as you're making the right steps and you're going the right direction. If you're really in a pinch, you can try and change one side a bit and then change the other side and sort of meet in the middle, and just bring everything down even to just theta, right? Not even 2 theta, and that would work as well. So that's part A done. When we look at part B, I mean, we see the word hence. It's a big clue, right? This part of the equation, at least, will be in the identity, and you just need to replace. So in my equation, if I see this expression on the left, and I know from the top that I can always replace that with 2 cot 2 theta because it's an identity, I'm going to replace in this equation. Oops. So instead of cos 3 theta over sine theta plus blah 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 equaling 4, it's just going to be 2 cot 2 theta equals 4. There's my first mark as well. So 2 cot 2 theta equals 4. Hopefully you can recognize this as just a standard trig. Cot is 1 over tan. And we get all our solutions. And make sure, however you get all your solutions, you're getting them. Right? I don't know exactly how you do that. Here we have theta being between 90 and 180. So I will just say that 2 theta is between 360 and 180. Do my inverse function, calculator, given degrees, so inverse tan of 1/2. It also said 1 decimal place. 26.6. I will do 2dp for the moment because I'm not finished. I'm going to divide by 2. Yeah, I'm not going to go through finding all the solutions. You do how you do it. For me, tan, I just keep adding 180 and taking away 180. Pretty simple. I'm just looking in this range. I don't think I have any more. No more. I should cross that one out. theta is 103.3 degrees, and that's it. I'm done. Right? I would just always check. It's sometimes a sneaky mark if you've used an identity. Possibly your solution doesn't work in the original equation, right? If I had a theta that made sine theta or cos theta equal 0, then that wouldn't work. This is fine. So I define solution. And if you want, if you got the time in an exam, you just store it as x in your calculator and just put it in that original equation, right? Cos 3x over cos x over sine x, and finish it off, and it will work out. And it's a nice trick. Right. Let's look at another example. Okay. So give it a quick read. You'll see again this structure: part A identity, part B equation. Very common. Okay. So again, I'm going to make the same decision as before. Do I start on the left or do I start on the right? And actually, I don't think it's as obvious in this case. I notice there's 2 thetas and there's thetas. So I'm going to want to bring everything down to theta. So I'm going to use a double angle over here and use a double angle over here. And when I think about double angle, well, I remember how cos 2 theta actually had 3 different options which formula to use. So instead of trying to guess which one to use and just getting lucky, why not just start on the right-hand side? Right? There's only one way to simplify sine 2 theta, and that is 2 sine theta cos theta. And my other sort of method is bring everything in terms of sine and cos, right? No tan. Unless you see directly that you're going to have something like this, tan squared plus 1. It's usually just better to have in terms of sine and cos. And here you see that you will get a cos cancelling with the cos over there, and I'll just get 2 sine squared theta. And now maybe that makes it more clear which identity I should use for the left, right? So 2 sine squared theta can't really be simplified anymore. I'll go over to the left side. I want to use the identity that replaces cos with an expression involving sine squared, because this is sine squared and no cos squared. And yeah, that just works out. You are totally allowed to do this, okay? You do not have to start with the right and with the left, as long as you're clear. The right equals this, the left also this, therefore they are the same thing. Yeah, very quick. Part B, going to replace. So look at my equation. This one has an example where we have thetas here and x's here, so you do have to be careful again. Question is, what do I replace? Right, something in this equation will relate to one of the sides of the identity. And I see 1 minus cos 2x, which could replace the left. Or I guess you've kind of got a tan x sine 2x over here, but the fact there's also another tan there, it's not quite as clean. So I'm going to replace the 1 minus cos with the tan sine 2 theta. And actually, it works out, if you compare the blue sort of expressions, sometimes x might have to be like 2 theta or 3 theta, but if I just directly replace x and theta, they will match up. So it's a nice straight swap. So I will have tan x sine 2x. So that is x squared x minus 5 times by, forgot what it was, tan x sine 2x is equal to, not identical to, oops, it's an equation, equals 3 tan squared sine 2. It's quite ugly. There's a lot going on. You might stare at it for a bit, think about expanding. I'd caution against that, because then you've got many different terms and it looks really horrible. Look for something else maybe, and you might notice there's common terms on both sides. And I'm definitely going to use that. Remember, we never divide by an unknown in equations. We can never do that, because that unknown could be 0 and then you're losing solutions. So instead, just take your common term that you were going to divide by and factorize it out instead, right? So subtract over and make one side equal 0. And I can factorize. So I've got tan common, I've got sine 2x common. Notice I still haven't expanded the bracket yet because I don't know if it's the right thing to do until I've done a bit more work. It might be, but it's just helping me see things a bit more clearer, keeping it factorized for now. Tan sine 2x minus 3. And actually, I can see there was absolutely no need to expand the bracket because it all comes back outside again, and I would have just got the same answer in a lot more steps. Now I have a product, right? I've got 1 bracket, 2 bracket, 3 brackets equal 0. So I need to say that any one of those could be 0 and get all my solutions. Just going to remind myself of what range x could be in. X is between minus pi by 2 and pi by 2. Okay. So tan x being 0 would lead to x being 0, only solution in that range. Sine 2x being 0, well, 2x is now between pi and minus pi. Not inclusive though. So I would be allowed to use the end ones. They would work as solutions, but they're not in the range. So just x equals 0 again, which means the rest of my solutions are going to come from this. Now, if you've done enough work in class on the sort of basic techniques, you might recognize this. If not, well, what you should look for is 2 different trig functions. That's not nice. Can I relate them somehow? There's a 5 over here as well, so I can't even add the 3 and change sine and cos. And hopefully you remember that sec squared is 1 plus tan squared x. And if you were to replace that, I'd have a quadratic in tan x. So 1 plus tan squared x minus 5 minus 3 tan x equals 0. If you didn't spot that and you just wanted to go with the old sort of reliable, make everything in terms of sine and cos, you would still get the solutions, I believe. But I think it's a lot more horrible. And from memory, you might even end up with a cubic here. So this is definitely the way to go. Tan squared x minus 3 tan x minus 4 equals 0. This is quadratic. Solve it however you please. Tan x minus 4. Tan x plus 1. I don't bother writing the u. You can if you want. Tan x either equals 4 or negative 1. Again, in this range, tan x equaling 4, I'm going to have to use my calculator. That's not a nice value. Does it say, give any non-exact answers 3dp? No, 3dp. 75.964 degrees. Whoa, hold on, that's degrees. My question was in radians, wasn't it? 1.326. Be better. Almost lost a mark there. Okay. 56. And then the other one. Maybe you know it, maybe you don't, but inverse tan negative 1 would be negative pi by 4. I believe that is in the range, and if I add pi or minus pi, I will then be outside the range. So I reckon I have 3 solutions there. And it's radians. Okay. I hope that kind of helps. Just remember to take a look at both sides when you do identities. Think what you have and what you're aiming for and what steps you can take in between. And if you're really stuck, you do what I did here and you just change both sides and eventually meet in the middle. So maybe I'll do a video more with modelling with trig later if that would be helpful.